Okay, so in the last class we looked at Turing machine, the beautiful machine, right? And you saw the how do we construct, you know, Turing machine for accepting certain kind of languages which are known as recursively enumerable languages. And also you also saw how to do computations, like for example, addition of two numbers and so on and so forth, right? Now, directly designing those kind of Turing machines sometimes is tricky if the problem is very complex. So there are certain variations of Turing machines which are equivalent in terms of the power. The deterministic Turing machine that I talked about last class and all these variations are same in terms of power. But these ones variations are easy to design. So basically, if there is a complicated problem or a bit complex problem, you can use these kind of machines. So rather than showing the actual Turing machine, you use these variations to show that how to solve that particular problem, right? So that's why these are very useful. So while discussing these, I will give you a brief overview. I'm not going to discuss in too many details, but at least you should have some understanding. So there are different kind of Turing machines that are possible, different variations of Turing machines, right? That's number one. Number two, uh, after talking about it, then I am going to talk about what is known as universal Turing machine. So one Turing machine which can simulate another Turing machine. So using these ideas of variations of Turing machine. So we can talk about those things. And then finally, I'm going to show that there are more problems or more languages than the number of Turing machines using simple idea of countable and uncountable from your calculus class. If you have not done that in calculus, so I can quickly do that 5-10 minutes. That's okay. It's a very beautiful, simple idea. Okay. And after that, so once the Turing machine business is done, then I'm going to look at grammar. So because you see all these four machines, they accept certain kind of languages, right? And each language has a grammar. So from there, how do we define a grammar of a language, and how using the grammar and using the production rules of the grammar, I can generate the language. I'll show you those things. Okay, that connection. And basically, there are four kind of grammars. So there are four kind of machines, right? Finite automata, push-down automata, linear bounded automata, and Turing machine. And each of these four machines, there is a corresponding language. The first language is regular language, then context-free language, context-sensitive language, and recursively enumerable language, right? So all these four languages are there. Then correspondingly, there are grammars. So grammars are like, first one is regular grammar, context-free grammar, context-sensitive grammar, and unrestricted grammar. So there are four grammars. Okay. So how do we? So this is how we are going to summarize the whole stuff. So essentially, I'm going to use 5 PPTs, and it will be done pretty easily. It's very easy concept. So you see, मूल तत्व को पकड़ना है, right? Rather than going into too many things, you should be able to understand, because you see as I mentioned earlier also, the fundamental, very very fundamental thing is all these, that whole computer science can be summarized with these four machines. Okay, and the variations of these, there are different kind of variations. For example, there is something known as cellular automata, CA. It's very useful. So one dimensional block cellular automata is equivalent to Turing machine, and this cellular automata can be used, for example, in controlling the crowd management can be done as an application. In fact, one of my friend, they have managed crowd in this Mela in Madhya Pradesh, right? Kumbh Mela. So they have actually controlled the crowd using CA-based techniques. Okay, beautiful connections. It's all mathematics. Use mathematics, develop a system, and run a business. Right? It's all up to you what you want to do. Okay. So let me show you. Let me start this. Again, thanks to Professor Bush for using his slides. Okay. Okay. So in fact, during thesis, what Turing thesis is that any computation carried out by mechanical means. Remember, I told you that Turing misunderstood the word mechanical, right? He misunderstood this word, and that's how he thought of creating this Turing machine. So any computation carried out by mechanical means can be performed by a Turing machine. And in fact, what is an algorithm? Algorithm for a problem is a Turing machine which solves a problem. So algorithm describes the steps of the mechanical means. So this is easily translated to computational steps of a Turing machine. So when we say there exists an algorithm, we mean there exists a Turing machine that executes the algorithm. Now, so what are these variations that are possible on these Turing machines? So first one is what you see. So now if you look at the picture of Turing machine, there is a tape, infinite tape, head which is reading or writing, and write. So basically, and the state change, right? You state change from one state to other state. What variations you can think? So somebody will say that, okay, rather than using one tape, I will use two tapes. Somebody will say I'll use three tapes. Fine. So there is a Turing machine with multiple number of tapes. Okay. So that variation is there, right? Similarly, somebody will say that why you are using one-dimensional tape? I may use two-dimensional tape. That is also a variation, right? So each point, basically there is variable x comma y kind of thing, right? Here it is only single point, right? Single box. Here it is, you can have that kind of thing. So, two-dimensional tape or d-dimensional tape is also possible. Three-dimensional tape, four-dimensional tape, all kind of variations, right? So some of these easy variations can be done, but they are quite useful. For example, if you are doing certain computations, you can take certain portion of it and put it on one tape, for example, right? Take another portion and put it in another tape. And so your computation will be easy, it can be performed easily, right? So you can basically, rather if you have only single tape, many times it is difficult to manage the whole computation or solve a problem using Turing machine. But if you have multiple tapes or certain more dimensions in the tape or many other variations, then it's really useful actually. So let me show you. So this is our standard model, right? Infinite tape, and head can move left or right, and there is a control unit, which is deterministic choice. As I mentioned, there is a non-deterministic Turing machine also. Okay, so that variation is there. Now, first, very simple thing. I am going to make certain changes in the head. I will say that head. Right now, head can do two functions: either move right or you move left. I will say that it will move left, it will move right, or also it may stay there. Stay option machine. That's a very simple modification. So if first is stay option. Similarly, it could be semi-infinite tape, offline, multi-tape, multi-dimensional, and non-deterministic, right? See, these are all different classes of Turing machines. I am not listing all different possibilities, but few of them, of course. As I mentioned, the cellular automata, block cellular automata, those kind of things are also equivalent to Turing machines. So, I'm not looking. So some of these basic ideas I'm going to tell you. The first one is stay option. But in terms of computing power, all these machines have the same computing power. That can be proved. So let me show you. Stay option. So now movement of the head is left, right, or stay. L or S. These are the possible head movements. Okay. So now you see this mean here is a transition from state Q1 after reading A, replace it with B, and stay there itself. Do not move. Head is not moving, right? That can be done. But the state is changing. You see, from time 1 to time 2, A is replaced with B and no change. So one can clearly say that stay option machines have the same power with the standard Turing machine. And how do we can do this? Two parts. Of course, proof I am not very much interested right now. I want to convey the idea that what are the variations that are possible, okay? And then, of course, if you want or if you are more enthusiastic, you can look at the proof. Of course, stay option machine simulate any other standard Turing machine because any standard Turing machine is also a stay option machine. How? Right, I mean, which is trivial thing, right? So there is one more thing, right? The head is left, right, and stay, right? And can you simulate a stay operation with only two movement, left or right? Yes. So if stay means you go to left and come back to right, right? So that also can be done, right? So there is obviously this stay is quite useful. I mean, so that is one thing. So you see, for example, this stay option machine here, from state Q1, A is going to be move left and then move right, right? So for every possible tape symbol X, you can do this, okay? That is a stay option machine. Next, Now, I am not worrying about any of these, leave it, the proof. Okay, multiple track. So here, one tape, but tape has multiple track. That is also a possibility. Okay, multiple tracks. So there are two tracks, track one, track two. So head is reading two symbols at a time, reading A comma B, and do the operations accordingly, right? Reading two things, similarly reading three, if there are three tracks or certain number of tracks, so n number of tracks are possible, right? Those kind of things are possible. But sometimes, so what I'm saying that when you use multiple tracks, you can solve more complex problems, right? So that's why these things are really useful. Then semi-infinite. So one side so a standard Turing machine has two infinite things, right? Either this way or this way you can go. So one way it is finite, the other way it's infinite. Okay. Is happening? Anyway, so it's a semi-infinite tape. So basically, while simulations, you can say that once you arrive at this, you go back. So in infinite, so you can actually fuse the infinite tape can be converted into semi-infinite, right? You can go back, from there. So that kind of modifications are possible. Then we have offline machine. So input string appears on input file only. You read only once input, and then rest of things are here. This is offline machine. So you're only allowed to read the machine only once, right? That is another variation. Okay, I'm not worrying about the details, just idea that there are different variations possible. Multi-tape, so now control unit. So tape one, you have input string, tape two, you have something. So input string appears on tape one, and there is another something on tape two, and so on. I'll show you how we'll use this idea later on. Okay. Okay. So that's all about variations. So easy, right? You got some ideas. Now, the language. No, same power doesn't means same complexity in terms of time, right? Are you aware of big O notation? No. कहाँ पढ़ा है? Okay, DSA. Who invented it? So how do you define? So if a function f of n is equal to big O of g of n, that means mod of f of n is less than or equal to k times mod of g of n, right? Where k is known as Borel constant. Yes. I am sure the person who has ever taught you will never teach you these things, right? K is Borel constant. And it's a very nice book if you can read Order of Infinity by G.H. Hardy. If you're really fascinated by these things. Order of Infinity by G.H. Hardy. And as I mentioned to you earlier also, that Donald Knuth actually used these things in computer science first time in that book, so The Art of Computer Programming, and it has become de facto standard since then, right? By the way, Donald Knuth has done a lot of his PhD thesis was on this finite field business, So it's a beautiful thing there, especially some sort of geometry. Geometry over finite fields is a much more difficult branch. Okay. So he worked with Marshall Hall, so there are, I think, yeah, so 3 PhD students of Marshall Hall. So one is Donald Knuth, who shaped the entire computer science, got the Turing Award just for writing that book, you see, one book. And the second one is Rob Kelderbank, who was AT&T Bell Labs, vice president for research, and after that he moved to Princeton, and I think right now he's the dean of Duke of engineering at Duke University. Anyway, so because I have some personal interaction with these people, so I tell you about it. Anyway, so the complexity is very, very important. So this time complexity might be different. Okay, that's what I want to say. So this is two-dimensional Turing, so multi-dimensional Turing machine. For example, two-dimensional. So moves are left, right, up and down. That is a possibility, right, for the head. Okay, that kind of variation is possible. And non-deterministic choice. So non-deterministic Turing machine, for one input you have multiple choice. The same thing. Right. I think that's all. We are done with this business. बाकी ये सब पढ़ने की जरूरत नहीं है, right? So now, okay, now we come to universal Turing machine. This idea is really interesting. So essentially now I am going to show you that if I count number of Turing machines, I can count how many Turing machines are there by mapping each Turing machine to a binary string of 0 and 1. That is a possibility. Turing machine can be mapped to a binary string. Okay, and so all collection of all Turing machines I can count. It's a countable set. But then the number of problems, actually the languages, are more than the number of Turing machines. This is what I'm going to show you. That means there are problems for which we cannot have a Turing machine. This is the key idea that I want to conclude. And for that, I'm going to use countable and countable business. But before that, I will show you what do you mean by, what is the meaning of the universal Turing machine and how you can simulate one machine with another machine. Okay. So again, thanks to Professor Bush. So a limitation of Turing machine. Turing machines are hardwired. They execute only one program, right? But real computers are reprogrammable. That's an idea. So what we should do? Solution is a universal Turing machine. So its attributes are reprogrammable machine and simulates any other Turing machine. So how do we do this simulation? Here I am going to use this variation of Turing machines actually. It's a very, very important thing to see. So what we do, so this universal Turing machine simulates any other Turing machine. So input of the universal Turing machine is a description of the transitions of M. So basically, if you look at a Turing machine, what are the key things? Transitions, right? And what else? Input string and transitions. What are the rules? Essentially, transitions are nothing but a computer program. Actually, you can think of a program. You're writing a program for actually, doing the stuff from the Turing machine. Okay. So now, if you take 3 tapes, so universal Turing machine can have 3 tapes. Tape 1, description of the machine. Tape 2, tape contents of the machine. And states. Also, we need to worry about the states. Like that, I can simulate. So universal Turing machine, which can have 3 tapes, can simulate some other Turing machine, which is some standard Turing machine I can think of. Okay. Now we describe Turing machine M as a string of symbols. In fact, first I need to look at alphabet. So you see, Turing machine will have some alphabet A, B, C, D, whatever, right? I can encode them with number of ones. A as 1, B as 1, 1, C as 1, 1, 1, D as 1, 1, 1, and so on. Fine. Easy encoding. Because alphabet is the first thing. I need to describe it. So each alphabet, I can describe it certain number of ones. Okay, I do this mapping. Okay. Next, state encoding. So there are states Q1, Q2, Q3, Q4, and so on. Them also I have described it by 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and so on. No matter how many states are there, you just map. Now you can see that here also I'm using number of ones. There also I'm using number of ones in the alphabet. So then of course we require some sort of delimiter which can distinguish, I'm going to talk about it. Then head movement is either left or right. Left means 1, right means double 1. Okay. Fine. Next, transition encoding. Now these are transitions. Delta of Q1 A is Q2 BL. How do we handle this? So state Q1. Now I'm going to use separator here. 0 is as a separator here. State 0 is a separator. Alphabet A is 1. Separator 1, 1 is then another state. Then separator B is another symbol. 1, 1. Separator 0 and head. So that means I'm just giving you examples, right? How we can map. So essentially that means each Turing machine can be converted into a binary string. Because states we are taking care in terms of binary string. Alphabet I am converting into binary strings. Actually, those are only ones, right? But overall, transitions are nothing but the actual thing which is happening, and they are also in terms of binary strings, right? So now, if there are two transitions, so this and this, you use 00 as a separator. Okay? A multiple transition, you can use more separators, 000 as a separator, and so on. Essentially, that means tape 1 contents of the universal machine, binary encoding of the simulated machine. So you can have the whole thing on this machine, the conversion, right? Next. So that means essentially, summary is that a Turing machine is described with a binary strings of zeros and ones. Okay. You can convert every Turing machine into a binary string of 0 and 1, right? Fine. Next. Therefore, the set of Turing machine forms a language. Because language definition is what? Bunch of strings over some alphabet. Here alphabet is 0 and 1, you can assume. Right? So that means set of all Turing machine forms a language. So each string of this language is the binary encoding of a Turing machine. Okay? That is a very key idea. So that means it can be described L as, I mean, of course, I have written very short, but you see, L is equal to whatever length is, right? Some binary string, comma, another binary string, another binary string. Each binary string is nothing but a one Turing machine. So that means we have, so collection of Turing machine forms a language. Any question here? That's very straightforward. Now we come to high school mathematics, right? Countable set. Now I'm going to show you if a set S is countable and infinite, its power set is uncountable. What do you mean by countable and uncountable? Countable means we can count. If things are finite, you can always count. How many people are there in the class? Very few, I mean, right? Maybe 60 today, I guess. You can count. Tomorrow, if there are 100, you can count. So any finite set, you can easily count, right? So a set which is infinite, we say that if it is finite, anyway you can count. A set which is infinite, we say that it is countable if you can count every member there. That means if I take first element from that set, I will map it to 1. If I take second element, I will map it to 2. If I take third element, I will map it to 3, and so on. That means what we are doing when we are counting means, you give me a number, I say, okay, 1. You give another one, I say 2. Give another one, I say 3, and so on. So you can count. That means you're establishing one-to-one correspondence with set of natural numbers to that set. If you can find one-to-one correspondence from the set of natural numbers to that set, one-to-one correspondence means there exists a function which is one-to-one and onto from set of natural numbers to that infinite set, then we say that that set is countable. Okay. If you cannot do this correspondence, the set is uncountable. Very simple. Common layman, you can even teach these things to some auto wala on the road, right? Countable and uncountable is a very easy concept. Now you see the beauty. I'll give you a couple of examples. The countable set, there is a one-to-one correspondence of elements of set to natural numbers, right? Positive integers. So set of even integers is countable because function is f of n is equal to 2n, which is 1-to-1 and onto. You give me 0, I will give you 1. You give me 2, I will give you 2. You give me 4, I will give you 3. You give me 6, I give you 4. Right? Give me a number, I will say 1. You give me another number, I will say 2, and so on. So there is an association to set of natural numbers. So these are countable. What about set of rational numbers? Are they countable? Set of rational numbers, they are infinite. And you know that they form a field. You can do all the 4 operations: addition, subtraction, multiplication, division with the set of rational numbers, right? But are they countable? Any idea? Why do you think it is no? So this, of course, if you look at initially, you feel that how do we make a corresponding set of natural numbers. See the common sense. You only require common sense. You see how we can do it. So what I'm going to do. So if you count it like this, okay, 1, 2, 1 by 1, 1 by 2, 1 by 3, and so on, 1, 2, 3. I mean, you will be in trouble. So we will never count 2 by 1, 2 by 2, 2 by 3. So there is a problem. So I'm sure if somebody sitting in a village in Anand can solve this problem. So what is a better approach? I just arrange them in this nice form. 1 by 1, 1 by 2, 1 by 3, 1 by 4, and so on. 2 by 1, 2 by 2, 2 by 3, and so on. 3 by 1, 3 by 2, 3 by 3, 3 by 1, and so on. 4 by like this array. Okay. Done? Now can you count this array? Yes, easily. How? Using this approach. 1, 2, 3, 4, 5, 6, 7, and so on. Right? But then you will say that what about negative numbers? You just insert in between and again do the same thing. Then you say that what about 0? I put in the 0 first. You start from 0 and then you start counting like this, right? We are done. Any question? The set of rational numbers are countable by common sense, right? The question comes, the beauty. What is the beauty? Give me the bijection I am talking about. Give me the example of that one-to-one and onto function which maps natural numbers to these numbers. Can you give me this? So it's a nice tea time problem. Can you give me a one-to-one and onto function which take every rational number and map it to? So from natural numbers we have the. So one way I'm telling you a hint could be what we call it as. For example, in this set we say the height of the number. 1, 1, you just add numerator and denominator. So 1, 1 is 1 plus 1 is 2. 1 by 2. 1 by 2 is 3. 2 by 1 is 3. That's another one. 3 plus 1 is 4. 2 plus 2 is 4. 3 plus 1 is 4. You see, this is one kind of height you can define for each number. So I'm just giving you certain hints. How do we define, right? From natural numbers, you have to map somehow to this set. So it's an interesting, non-trivial problem to find a one-to-one and onto function which can map each rational number to set of natural numbers. Okay? So this is something really very, very easy thing. I mean, not easy, but non-trivial, but beautiful thing, right? So you can do that. So that means set of rational numbers is countable. Fine. And you can say that this is a correspondence. Of course, 0 you can put in the first, right? Now find the function. You can write down the numbers to say then find the functions, How do you find the function? I mean, actually here in this case all positive, but if you can include negatives and 0 as well. So we are able to count rational numbers because there is an enumeration procedure for this counting. So if S is a set of strings or language, an enumerator for S is a Turing machine that generates on the tape all the strings of S one by one. I'm going to give you an idea about if there is an infinite language, how will you count it? So basically, you can go by length of the string as a mapping to the natural numbers. So length 0, of course, I mean, just empty string. Then length 1, suppose alphabet is 0, 1. So length 1, a string will be 0, 1. Length 2, a string will be 0, 0, 0, 1, 1, 0, 1, 1. Right. Similarly, like that, you can have this kind of correspondence, right? So I'm saying that with the length, you can actually develop a enumeration procedure for counting in the language. So let me show you. So I'm saying that this set of strings ABC plus is countable. We'll describe an enumerator for S. Enumerator means which can enumerate. So proceed the strings in lexicographic order. This is not going to work, but what we are going to work is length. Produce all strings of length 1, then produce all strings of length 2, produce all strings of length 3, and so on. So length is sort of mapping to the natural numbers. You can think, right? That kind of connection is there. So this is how you order is there, right? You can start with First number, second, third, fourth, 5, 6, you can keep on counting because this is, we keep on continuing, right? That way. So essentially, we arrive at this result that the set of all Turing machines is countable because it is all, collection of binary strings, right? You just enumerate in terms with respect to the length, you can find an enumerator for it. Next, I'm going to talk about uncountable set. So we'll prove that there is a language L prime which is not accepted by any Turing machine. And the technique is that, so Turing machines are countable and languages are uncountable. And that is the key difference. So I'll show you. So only last part is left. If S is an infinite countable set, its power set is uncountable. A set is uncountable if it is not countable, right? So we'll prove that there is a language which is not accepted by a Turing machine. So essentially, I'm going to show you this result. And the trick that is used is very, very popular in mathematics, developed by, you must have read this somewhere in JEE, IT JEE, no? Countable and countable, anyway. Let me show you. If S is an infinite countable set, then its power set is uncountable. So since S is countable, we can write every element as S1, S2, S3. I think here you need to pay attention for 3-4 minutes because this is very, very important. And at the first time when you look at this, people do not understand what is happening. Okay. This is known as Cantor diagonalization argument. When Cantor actually gave these kind of ideas, and also, he talks about many infinities. There were a lot of issues. People were saying this guy is mad. I don't know what he's talking about, right? So it's very, really interesting stuff. So observe that. So S is a countable. We can write elements as S1, S2, S3, whatever, right? The power set of S will have pi. Then all power set, all elements of size 1, 2, 3, and so on. You can write like this. Essentially, every power set you can represent by binary strings. Do you agree with this? I think we have talked about this earlier also. These are the power set elements. This can be represented. So you can mention all the binary encoding, all the elements of the set S. Whether it is present or absent, you can write it as a 1, 0, right? So every power set element can be written as a binary string. This is a very nice correspondence, and it's quite useful also. So observation is every infinite binary string corresponds to an element of the power set. So wherever there is a 1, I will take that member of the set. So for example, here 1, 0, 0, 1, 1, 0 means first element of the set, fourth, fifth, sixth, and so on, right? Element of the power set, right? If S is S1, S2, S3, and so on, we can actually write every element of the power set as a binary string. Now the proof starts. Now I just need your 2 to 3 minute attention. If you are feeling sleepy or whatever, just shake your head for a few minutes and be ready. It's very, very important. Nice. You observe this is very beautiful idea, what I'm going to show you. Okay. Now I'm going to show that the power set is uncountable. Remember, S is a countable set. So I can write down every element as S1, S2, S3, and so on. Means each element has a correspondence with natural numbers. First one is S1, second one is S2, third one is S3, and so on, right? That is there. I have to show that the power set is uncountable. But now I am assuming that I'm going to use the contradiction method, which is very common. Assume that the power set is countable. If I assume that the power set is countable, I can write down its element also as, say, with correspondence with, so I can write down power set as T1, T2, T3, and so on. Right, the first element of the power set, second element, third element, and so on. So I'm assuming power set is countable, and this is the enumeration procedure. Now what? Now comes the beauty. We know that every element of the power set has a corresponds to a binary string. So T1 will have some binary string, T2 will have some binary. These are just random binary strings I've written. It could be anything. Okay. Now, this is a supposed representation. So T1, T2, T3, T4, T5, and so on. We can keep on going. Okay. These are the binary strings. Now, So our assumption is power set is countable. Every element can be written, one, so T1 corresponds to 1, T2 corresponds to 2, T3 corresponds to 3, and so on. There is a correspondence, right? I have written everything. So I'm saying that this will keep on going, right? Now I'm saying that means now I'm going to give an example of a element which is a binary string, but which is not in this set. Okay? How it is possible? So this power set corresponds to binary strings, right? I have to basically give you an example of a string. I mean, think about it. It's a beautiful idea. Now I'm going to give you now I'm saying that I am taking a binary string T. I'm saying that look at this binary string T, how do we construct this binary string? The first element here is the complement of the first element there. So T1, the first element is, I will look at this diagonal elements in this array. The first element is 1. I will take the opposite, which is 0 here. I take the second element here, T2, which is 1. I take it the opposite, which is 0 here. Right. Then I take the T3. Here it is 0. I'll take it 1 here. Okay. Then here you look at T4, it is 0. I'll take it 1. And like this, we can continue. So I have produced an element T, which is a binary string by this procedure, right? Now my claim is that this T can never belong to this list. Obviously, right? Do you agree with me? The way it is constructed, right? Because if it belongs to, say, ith element, it will differ at that diagonally, ii element will be different, right? Because of the way it is constructed. So that means this procedure is faulty. I mean, this our, we are going to trouble, right? So this is a contradiction, right? So that means we started with the opposite thing and we arrive at a, right? So we produce a string which is not in the set, right? So our assumption is wrong. So this power set is uncountable. I know some of you may still not be able to understand it. Yes. Any question? So this is a very famous argument. It is known as Cantor diagonalization argument. We are producing an element opposite to the diagonal. The same idea you can use to show that set of open interval 0, 1 is countable or uncountable. Real numbers, countable or uncountable. All these questions you can do. There is a very nice actually website which discusses these proofs based on this Cantor diagonalization argument, right? So you can look at it, right? And I think these things should have been taught at your IIT JEE level. I don't know why they are not teaching it. Kota mein padhaya gaya? So this is very interesting. I think which book you studied for calculus? Thomas. Thomas is just 1 week, it's a high school book. If you have not looked at the book by G.H. Hardy, very nice book, Hobson, Theory of Functions of Real Variables. Beautiful books, you will enjoy. So anyway. So we are able to produce, so I think, yeah, this is all done. So the application is a language, the set of all strings, infinite and countable. Any language is a subset here. The power set contains all languages, which is uncountable, right? So there are more languages than the number of Turing machines. I think that's all for this. We can finish. Got the idea? Now something really nice and easy. It's a very easy thing now. We are going to tell you about what is known as grammar. So just like that, each language, English language has a grammar. Sanskrit language has a grammar, right? And so each of you must read Sanskrit. I am telling you again and again, but anyway. So, can you create a chat GPT for Gujarati language? That is a challenge where you will require all these Sanskrit ideas, right? And you see, if you create that business in India, so I mean, of course, Gujarat, how many people are there total? 5 crore, 6 crore, 7 crore. If they are using this chat GPT, you see how much business you can create, right? Look at any Hindi, English, Indian language. You can create chat GPT for that. You will be making a lot of money. Just give me 2%, right? So, anyway, so context-free languages. So I'm going to talk about first the grammar. Actually, see the context-free languages. Uh, so they have context-free grammar. So actually, you know that the corresponding machine is pushed-on automata, right? So context-free grammars. Let me show you an example. Forget all this nonsense. Look at this example. So here the grammar, there are two production rules, S going to ASB and S going to lambda. S is known as variable, capital S is known as variable. Small letters A and B are known as terminals. Okay, this is the common language they use. Okay, and lambda is, this sometime maybe lambda. So there are these two production rules. Using these production rules, what language it can generate, I am going to ask. So it's very easy. What I can do, the first string is lambda itself. So how do we generate this string AB? S going to ASB. Then you use the second S going to lambda, you will get AB. Right? Sequentially, I am using these two production rules and we are getting AB language. AB string actually, you can generate. So if I ask you, so using these two things, if I go and can I generate some other? So what I can do, S going to ASB, and again you use the same first rule at there. You will get AASBB, and then at S you use lambda again, so you get AABB, right? This one, right? So this is something nice, right? From these production rules, applying sequentially, you can get bunch of strings. So essentially, you can get all these things. So finally, you will arrive at the language of this. So using these two production rules, you can generate all these languages for any n. So this is the language of the grammar. Simple, beautiful, very simple, right? From the language, I'm able to, from the grammar, I'm able to find the language. Another popular question that is asked, given a language, find the grammar. So that is also interesting thing. And I think in your assignment too, we have talked about few of these things. So if I think, yeah, so probably, I think you have not done assignment 2 in the class, right? Tutorials abhi nahi hua na? Assignment 2, right? This is still left. Sorry, assignment 3, 4. Yeah, I am talking about 2 in this term, model of computation. Anyway, so this is the idea. Now, by putting certain restrictions on these production rules, these can be classified into 4 kind of grammars. Okay, so I'm going to talk about that. I mean, I think this generation of string is very easy task, right? Any high school person can do it, right? Or maybe class 6th. Huh? So ये सब बकवास है, it's simple actually, बार-बार घुमा के, it's the same thing. The formal definition is a grammar is set of 4 variables, V set of variables, T set of terminal symbols like small a, B, C and so on. There is a start variable and capital P set of production rules. In the previous example, there were only 2 production rules. Okay. So context-free grammar, there is a condition on each production rule. In case of context-free grammar, most of the production rules are, so all production rules are this form: left-hand side is 1 variable and right-hand side is string of variables and terminals. So there is a, left-hand side there is only 1 variable and right-hand side is combination of variables and terminals like ABC. That is there, right? So this is the example of, in this example, so actually those 2 production rules, I can this is a compact form. S going to ASB, pipe lambda means these are, same thing, right? S going to first one is S going to ASB, second one is S going to lambda. Using this pipe notation, you can write in a compact form. Okay. So these are those two production rules. Capital V is start variable. There is only one variable there. Terminal is only having A comma B, and the start variable is 1, right? So this is how you can identify. So language of the grammar is all those strings starting from the start variable in 0 or more derivations, you arrive at W. Okay. बाकी तो is all. By the way, now again, if there are more complicated production rules, sometime you go left derivation or you go right derivation. Every time you make a choice, use only left variable. Okay. And so that kind of will give you left derivation. And if you use always right, you will get a right derivation. Sometimes they may differ also. So there is a ambiguity in the grammar, right? So how to overcome all those things is out of scope of your current thing, right? So you don't worry about it. Later on, these things you will, if you are very much interested and excited, you want to learn about compiler construction, parser, and so on, then these things are very, very useful. Otherwise, it's okay. Okay. So I'm not, forget about all these things, not needed. Now, so I talked about context-free grammar. I gave you one example and formal definition. And now we are talking about linear grammars. So grammars with at most one variable at the right-hand side of the production rule. So for example, you see this production rule, there is only one variable on the right-hand side. This is a linear grammar. This is a linear grammar because there is only one variable on the right-hand side in all production rules, right? This is known as linear grammar. This is an example of a non-linear grammar. There are two production rules on the right, SS. This is an example of a non-linear grammar, okay? Another linear grammar. You see that right-hand side, there is only one variable, either A or B, okay? Now we can talk about right linear grammar and left linear grammar. So all productions have the form A going to X, B, or A going to X, which is a string of terminals. So this is right linear grammar, okay? So production is on the right. Variable is on the right, actually. And this is left linear grammar, okay? So linear grammar means there is only one variable on the right-hand side. And depending upon, its position, it is left or right, okay? It's a very simple thing. So regular grammar, a regular grammar is any left linear or right linear grammar. So this is an example of a regular grammar. This is an example of a regular grammar. So you see that one production is this, another production is this, another production is this, and then another is this. How many? 1, 2, 3, 4. 4 production rules are there, right? Okay, so regular grammars generate regular languages which are accepted by DFA. So then all kind of conversions are there. See, now you see, one can ask, I can give you one regular expression. I will say that, point out the DFA. So from that regular expression, you can also, there are different ways you can combine, you can get this answer. Regular expression, you can find the regular language. From regular language, you can find the regular grammar. From regular grammar, you can find the DFA. All these, one way or the other way, these kind of, things are possible. You see, there is and actually, obviously, as you say, as I mentioned earlier also, you can construct from the grammar, from this grammar, you can construct NFA. NFA is easy, right? If NFA is equal to DFA, then you can always do that conversion. So here is an example, you see, from these production rules, how many variables are there? S, A, B. 3 variables are there, right? So S, A, B are the 3 variables, and so 3 states, and this is the final state VF. And then you have these certain rules. How do we convert? So from the grammar, there is a way to construct the NFA. From NFA, you can construct the DFA, and so on. Plus, I think that's all. Now, I think one thing is left. Last slide. Chomsky hierarchy. Again, thanks to Professor Bush. I am not sure why that is missing. Linear bounded automata. So when the Turing machine, the space is limited. The working space is only this much. There are markers, and you are only allowed to do all the computation in this. So that means there is a more overhead you have to do in the transitions. More transitions will be needed to handle because now the space is limited. Okay. Now this is still an open problem. So some of you can try. Nobody knows. Non-deterministic LBAs have same power as deterministic LBAs. Linear bounded automata or not. So this is something which is open. Now, unrestricted grammar, when we are forming these production rules and there is no condition either on left or right. One's left side also is a combination of terminals and variables. Right hand side is also a combination of terminals and variables. It's unrestricted grammar. This has more power as Turing machine. Okay. Same thing because this generates, so strings are variables and terminals, strings are variables and terminals. When you restrict it, this is an example of unrestricted grammar. So a language is Turing acceptable if and only if it is generated by an unrestricted grammar. Context sensitive grammar, again, string of variables and terminals on left and right, but we have this condition that this size should be less than or equal to this size. This is coming because we have the limited space kind of condition, right? Linear bounded automata kind of thing. So context sensitive grammar. Next, so this is an example of context sensitive grammar. You know that A and B and Cn is okay. And we have, this is the Chomsky hierarchy. So regular grammar, so regular languages, context free, context sensitive, decidable, Turing stable, non-Turing stable. So there is a Turing barrier also. We saw that there are languages more than, and that's all. So now, challenge. The challenge is fail hoke dikhao. So can you get 0 marks? And then finally you get a grade towards the end. That is take that challenge, then you know how to convert the tables, right? That is possible. Okay. I should mention to you that in one of my class, there was a Korean student. And in fact, I was teaching this theory of computation. And towards the end of the exam, he said, and he came and told me that because of some personal reasons, he could not study properly. Is there any way to make A grade? So I told you get full marks in the final, and I will give you A grade. I mean, double A in your case, right? And he topped the whole exam, whole class. So I have given him double A. So that option is available to you also towards the end. But if you fail now, you have the option to recover. But can you take that challenge? Right? 0, and still you are able to make it. So that takes a lot of guts, right? See, people here, if they get only 2 marks less, 3 marks less. So I just met one person in one class, in course, he got 4 less marks, and he was crying. See, most of the big people who have changed the world, they're all, fail in the academic system, right? What is big deal? Right. So Albert Einstein, he failed. Thomas Alva Edison, he was kicked out of the school. Right. So there is no big deal, right? Take it as light. Enjoy the stuff, and I still am giving you an option to do things. Thanks. Wish you all good luck. And if you have any doubt, anything, WhatsApp is there. I'm available, right? Thanks.